Hello everyone, I'm Shivani and welcome to Civil series. This is the syllabus for strength of material, and in the strength of material, stresses and strain is the very important points. Okay, from the stresses and strain, most of the questions are asked. And next part is principal stresses. Then movements. Movement is also included in mechanics. Okay, mechanics is base for strength of material, but in the BMC exam, BMC sub engineer exam, mechanics is not included. Okay, so mechanics is the base for strength of material, but mechanics is not included as a subject in a sub engineer exam. Then next part is deflection, shear forces, torsion theory, bending theory, beam, theories of buckling of columns. These are the points which are to be covered in a strength of material. Before discussing or before starting the strength of material, first we'll discuss what is the strength of material first. Okay. First, the strength of material is comes from solid mechanics, and solid mechanics is a part of engineering science. Okay, engineering science is the biggest part. Under the engineering science, there are three parts, which is solid mechanics, fluid mechanics, and next is properties of material. For now, fluid mechanics and properties of materials, we not discuss about that here. We discuss about just the solid mechanics. Solid mechanics is divided into two parts. First is engineering mechanics and second is strength of material. First is engineering mechanics, second is strength of material. Engineering mechanics is related to rigid bodies. Okay, and strength of material is related to deformable bodies. So first of all, what is the rigid body? Okay, rigid body is that body in which the length before applying a load and length after applying a load and after removal of that applied load, the length before and length after is same in case of rigid bodies. And in case of deformable body, in case of deformable body, length before applying load and length after applying load, then after removal of that load, the length is not same in case of deformable bodies. In case of length, in case of depth, in case of width, the parameters are same. In case of depth and width, the parameters are same. Just we discuss all the properties in engineering mechanics related to rigid bodies, and in strength of material we'll discuss the properties with respect to deformable bodies. This is the simple difference between engineering mechanics and strength of material. Okay, so from here we'll start the actual syllabus related to strength of material. In that, first is stress. Stress is nothing but a internal resisting force applied on a body. Internal resisting force is that force which is applied by any body for some particular application of force on other side. Okay, internal resisting force is a inner side of resisting force for any action. Per unit cross sectional area is nothing but a stress, and this stress is denoted by Newton per mm square, or the unit for the stress is Newton per mm square and megapascal. Then stress is divided into two types. First is normal stress and second is shear stress. Second is shear stress. Normal stress is nothing but, first point, internal resisting force in a normal stress is perpendicular to cross-sectional area, and in case of shear stress, the internal resisting force is parallel to cross-sectional area. Then second, normal stress is divided into two types: direct stress, direct normal stress, and bending normal stress. Same in case of shear, it is divided into two types. First is direct shear stress and second is torsional shear stress. So this is the simplest explanation for the stress, and this part is also important. Most of the questions are asked from this part is the definition or the formula for the stress, and next is the unit. If they ask unit, then write it as a Newton per mm square, and if they ask in a Newton per meter square, then Newton per meter square is nothing but a Pascal, and if they want to change that Newton into dyne, then this is the conversion. 1 Newton is equals to 10 raised to 5 dyne. Okay, these kind of questions they ask from this part. Then second we move to strain. Then next is strain. Strain is nothing but a change in a dimension of any body. Change in a dimension of any body. Change in a dimension is possible when there is an application of some force on a body. Okay, change in a dimension to original dimension is nothing but a strain. And strain is a unitless quantity. Strain is unitless quantity. Strain is also a two types. First one is normal strain and second is shear strain. Second is shear strain. Normal strain is that strain in which change in dimension is possible. Change in dimension is possible, and in case of shear strain, change in shape is possible. Okay, so this is the simplest explanation for the strain, and here in case of a strain, most of the time they ask this formula, and sometimes they ask about the unit of strain. Then next is stress strain curve. Okay, in the stress strain curve, on the x-axis strain is there, and on the y-axis stress is there. Okay, remember that thing. If you draw any kind of graph, the independent quantity should be on a x-axis and dependent quantity is on a y-axis. Okay, stress is depend on strain, so that's why stress, we take stress on y-axis. Okay, so here this graph is related to mild steel. Okay, and for mild steel, after application of a force, first point we get, that point is limit of proportionality. Limit of proportionality, and that limit of proportionality is beyond which linear variation ceases. Means after the point A, limit of proportionality, the stress is directly proportional to strain, does not remain constant. Okay, up to point A, stress is directly proportional to strain. Up to point A, stress is directly proportional to strain, and this is nothing but a Hooke's law. Okay, this is nothing but a Hooke's law. Then next, B point. B point is nothing but a elastic limit, and in that elastic limit, maximum stress in which original length is regained. Okay, up to that point, if we release the force applied on a material or force applied on a mild steel, if we release that force, then that material come to its original position. Okay, up to point B, that thing is happen. The next, C point, which is upper yield point. Okay, the next, C, first is C dash. C dash is upper yield point, then C is the lower yield point, and C is the lower yield point, which is actual yield point. From that C, the material does not regain its original position after removal of applied force. Okay, C is the fixed point from where the material completely goes to plastic state. Then next, C to D. C to D is the part nothing but a perfectly plastic region or a yield plateau region, and that CD in that plastic strain is equals to 10 to 15 times of elastic strain. Then next, from D to E. From D to E, that path is nothing but a strain hardening zone. In that strain hardening zone, the strain increases fast. That's why stress also increases fast. Then next point is E, and that E point is ultimate stress point. Ultimate stress point, in that stress correspond to ultimate stress. In that This strain is 20% of mild steel. Mild steel, total mild steel strength is 100%, and up to the ultimate stress point, that strain is 20% here. This is the maximum point or maximum stress calculated on the mild steel, and that point is ultimate stress point. Then next, from E to F, that E to F is a necking region. In that necking region, the cross-sectional area of mild steel is drastically reduced. In that, the strain of that zone is nothing but a strain softening zone. D to E is strain hardening zone, and E to F is strain softening zone. Then last point is F. F is a fracture point. In that fracture point, stress about that point is a breaking stress, and strain about that point is a fracture strain. And strain is 25% of mild steel. Then one more point is important here. From starting of graph up to point B, there is an elastic region. After point B up to the point F, the region is plastic region. Then next, assumptions used in strength of material. First is the material is homogeneous and isotropic. Material is homogeneous and isotropic. So what is homogeneous and isotropic? Homogeneous is nothing but the same property in each and every point on a particular direction. Okay, consider this is in a body. Definition is same property in each and every point. Means this is one point, second, third, and fourth. These are the points on body. In each and every point, property is same, but in a particular direction. Means on this point in x direction, assume this as x direction, all the properties are same. Let's assume it as 1. Okay, and next, if here they said the property is same on each and every point but in a particular direction, means we consider this direction as a vertical, then the property for the vertical is same. Means for 2 the property is same. This is nothing but a homogeneous. Then in case of isotropic, the definition is same property in each and every direction at a particular point. Each and every direction means for every direction, for x and y on a particular point the property is same. Means for this 1, then for this 2, then for this 3. This is nothing but the isotropic. Then second, Hooke's law is valid here. Hooke's law is valid. Hooke's law is nothing but stress is directly proportional to strain. Then next assumption is prismatic section is considered. Prismatic section considered, non-prismatic section not considered, or non-prismatic section is neglected. Prismatic section is that section in which the dimensions are same or equal throughout, and this is nothing but a non-prismatic section which has no dimensions. Then fourth is self-weight. Self-weight is neglected. Self-weight is neglected, but surface force is considered. Okay, so these are the 4 assumptions used in the strength of material. Then next is property of material. In that, first property is ductility. First property is ductility. Second is malleability. Malleability. So there is a one short trick for ductility and malleability. Remember dW for ductility and MS for malleability. dW means ductility causes wires and malleability causes sheets. Okay, so here W for wire, S for sheets. For making a wires, tension is required, and for making a sheets, compression is required. So this is just the ductility and malleability. Remember only these 2 points. Then next, brittleness. So brittleness is nothing but a lack of ductility. Lack of ductility. Then next property, toughness. So toughness is nothing but a resistance against fracture. Toughness is resistance against fracture. Then next is resilience. So what is resilience? Resilience is nothing but an ability to absorb the energy, up to its elastic limit, and release that energy after unloading. Resilience is the ability to absorb the energy within elastic limit and release that energy after unloading. Okay. Then resilience has one formula. Resilience is equals to sigma square divided by 2E into V. Okay. And then modulus of resilience. Modulus of resilience is resilience per unit volume. So for modulus of resilience, sigma square divided by 2E. This is the formula. Then next is proof resilience. Proof resilience. Proof resilience is nothing but a maximum value of resilience. Proof resilience is nothing but a maximum value of resilience. So this is the formula for the proof resilience. This is Y. The next is fatigue and endurance limit. 6 number. Fatigue and endurance limit. Fatigue is due to the repetitive loading. Fatigue is due to the repetitive loading, and endurance limit is that limit in which maximum value of stress up to which no fatigue cracks are developed is nothing but a endurance limit. Then last is creep. So creep is nothing but a permanent deformations due to continuous loading with a time. Permanent deformation due to continuous loading with time, or the continuous deformation with respect to time is nothing but a creep. So these are the properties of a material. First is ductility, second is malleability, then brittleness, toughness, resilience, fatigue and endurance limit, and last is creep. All are the important. Most of the time the questions are asked from grip, and next from fatigue, endurance limit, and sometimes they ask this DW and MS. The next is deflection of bar due to axial loading. There are two type of condition. First, load applied gradually, and second is load applied suddenly. Okay, if load applied gradually, then deflection is delta L is equals to PL by AE. And next, if load applied suddenly, then delta L is equals to twice of PL by AE. These are the simple formulas when load applied gradually and suddenly. But the important point in that case is AE is nothing but axial rigidity. Second, same thing as per the AE, the thing is EI, which is flexural rigidity. Then next, AE by L is axial stiffness. Same for EI by L. This is nothing but a flexural stiffness. Okay, so these are the important terms in this formula: AE, EI, AE by L and EI by L. Then next is deflection of bar due to axial loading. There are again two conditions here with a varying diameter. There are two type of bars. First is cylindrical bar and second one is rectangular bar. Second is rectangular bar. So this is the cylindrical shape. So this is the cylindrical shape. Here the delta L for the cylindrical bar is 4 PL divided by pi D1 D2 into E. E is the Young's modulus. The next for the rectangular bar, this is the rectangular bar. Then this is the formula for deflection of rectangular bar. Delta L is equals to PL divided by ET in bracket B1 minus B2 into log of B1 by B2. So these are the two formulas for the deflection of bar due to axial loading. These two formulas are directly asked into the exam. So these formulas are important. Then next is Poisson's ratio. Poisson's ratio is represented by mu or 1 by m. Poisson's ratio is nothing but mu is equals to lateral strain to longitudinal strain. Okay, so lateral strain is with respect to the depth and longitudinal strain is with respect to the linear dimension, means with respect to the length parameter. Lateral strain is nothing but the minus of delta D by D, and so here this is lateral, and the next is longitudinal. For longitudinal strain, delta L by L. Then next, these are the some values for the Poisson's ratio. Mu for cork is 0. For rubber is 0.5. For mild steel 0.3. For concrete 0.15 to 0.20. For cast iron 0.23 to 0.27. And the values of Poisson's ratio are between minus 1.5 to 0.5. Minus 1.5 is for the polymer sheet and 0.5 for the rubber. The next formulas related to different loadings. So first of all, one more important formula is their Hooke's law. You know, Hooke's law is nothing but stress directly proportional to strain. But stress directly proportional to strain, there is one constant between this. So stress is equals to, or stress by strain is equals to Young's modulus. Okay, Young's modulus, or also called as a modulus of elasticity. Modulus of elasticity, and this represented by E, capital E. So this is the Hooke's law, and we use this formula for the further formulas. So first condition is when we apply a force on a body in a one direction, like this. On this body, the force is applied on a one direction as a tension force, and these are the formulas for the strain in x direction and strain in y direction. The next case, if the loading is applied on a two sides in x and y direction, then if force applied on a two side, then these are the formulas of strain about x-axis and strain about y-axis. Then third condition, if force is applied on a three sides, means x, y and z. So in all three directions the forces are applied, then this is the formulas for the strains applied in the x direction, applied in the y direction and z direction. So these are the three formulas. So remember, first condition, the forces applied only in a x direction. then this is the formula. Then in second, forces applied on both direction in x and y, and in third case, forces applied on a three directions x, y and z. Then these are the formulas for the strains with different loading conditions. Then next is volumetric strain. So volumetric strain is nothing but a ratio of change in a volume to original volume. So this is the formula for volumetric strain, and this is also a unitless quantity. Then next there are two formulas of volumetric strain in cylinder and volumetric strain in sphere. So these are the two formulas for cylinder and sphere for the volumetric strain. Elastic constant. There are different elastic constants for different material. So for homogeneous and isotropic material, elastic constants are 4 and 2. Here 2 are independent. Then second, for orthotropic material, elastic constants are 9 and 12. Here 12 are independent. Then next, anisotropic material. Elastic constants are 21 and infinite. Here 21 is independent. Okay. Then again, elastic constant is related to Hooke's law. There is one elastic constant which is Young's modulus or modulus of rigidity. But we discussed it earlier, so we are not discussing this here again. The next is bulk modulus. Bulk modulus is represented by K. Bulk modulus is nothing but a normal stress to volumetric strain. Normal stress to volumetric strain, sigma by epsilon V. Then next is shear modulus. Shear modulus is also called as modulus of rigidity. Modulus of rigidity represented by G. And shear modulus is nothing but a shear stress to shear strain, tau by phi. This is nothing but a shear modulus. Then next, these are the different formulas which is related to the Young's modulus or shear modulus, then bulk modulus and Poisson's ratio. By using all the four elastic constant, there are few formulas and which are very important. So first is E is equals to 2G 1 plus mu. Okay, here we calculate Young's modulus, shear modulus and Poisson's ratio. This is the first formula. Then second formula is E is equals to 3K in bracket 1 minus 2 mu. This is second formula. Then third formula I write here. So third formula is E is equals to 9 kg divided by 3K plus G. 9 kg divided by 3K plus G. Then last fourth formula is mu is equals to 3K minus 2G divided by 2G plus 6K. All the four formulas are important here. So you can write that formulas. So we can remove this for writing. You write that formulas. All the four formulas are important here. So write this and remember all the four formulas. And this bulk modulus and okay. So this is the important. So remember all this. The next point is then next is temperature stresses. Due to temperature, many changes are happening into the construction materials. If temperature is increased, then the material get enlarged by some dimension, and if the temperature get decreased by the regular temperature, then that material get reduced in a size. Okay, these are the simple effects due to the temperature stresses. Here first we discuss the formula related to temperature stress, and then second temperature strain. So for temperature stress, the formula is L alpha into delta T, and for strain alpha into delta T. Here alpha is nothing but a coefficient of thermal expansion. Coefficient of thermal expansion. Okay, and there are different values of thermal expansions. For mild steel and for concrete, the values of coefficient of thermal expansions are same, 12 into 10 raised to minus 6 per degree Celsius. For concrete, there is a range, 6 into 10 raised to minus 6 to 12 into 10 raised to minus 6 per degree Celsius. For copper, 16 into 10 raised to minus 6. For brass, 19 into 10 raised to minus 6. For aluminium, 23 into 10 raised to minus 6. So these are the values of coefficient of thermal expansion. What is beam? So beam is an horizontal structural member which is present in each and every building construction. So this is an horizontal member which is called as beam. Okay, beam contain two parts. If we cut this beam about its half or a mid span, about its length, then this is nothing but a neutral plane. This is nothing but a neutral plane. And if we cut this beam into a section, and this is the section of beam, if we take the half portion or if we cut this beam into the half, then this is nothing but a neutral axis for this beam. So neutral axis is for cross section and neutral plane is for the length or longitudinal section. Okay, so beam is nothing but a horizontal structural member or a flexural member, because in a beam bending happen, and beam carries a transverse loading. Beam carries a transverse loading along its neutral axis. Transverse loading. Transverse loading is nothing but a perpendicular to neutral axis. So this is the beam. Then next, type of supports. There are four types of support. First one is roller support. Roller support represent like this. This is the roller support, and roller support is with a single reaction which is vertical, means roller support resists the vertical reaction. Then second support is hinge support. So hinge support is represented like this. Hinge support is with two reactions. First one is vertical and second one is horizontal. Means hinge support resists the horizontal and vertical movement both. Then third is fixed support. So fixed support is represent like this, and fixed support has horizontal, vertical and movement, all the three reactions. Means it resists the movement of a beam in a horizontal, vertical and in a turning effect or like a movement effect. It resists all the three movements. Okay, all the three reactions in fixed support are resisted. Then third is guided roller support. Guided roller support. In the case of guided roller support, there are two type of support. First one is vertical guided roller support, and second one is guided horizontal guided roller support. The example of vertical guided roller support is horizontal, or the vertical guided roller support example is lift and shutter. And horizontal guided roller support example is horizontal sliding window. So these are the examples for the vertical guided roller support and horizontal guided roller support. Then next, type of beam. So there are 6 types of beam. First one is simply supported beam. So first one is simply supported beam. So this is simply supported beam, and simply supported beam is with roller support and hinge support. Simply supported beam. So first one is simply supported beam. On one side there is a hinge support, on another side there is roller support. Then next is overhanging beam. Overhanging beam has a two-side overhanging beam and one side overhanging beam, means one support is free. Okay, so this is the overhanging beam. Then next is cantilever beam. So cantilever beam means one support is with fixed support, one side is with fixed support, another side is free. So this is cantilever beam. Next is fixed beam, means both supports are fixed on both sides. So this is the fixed beam. Then next beam is continuous beam, means whichever the beam has more than two supports are called as continuous beam. So this is the continuous beam. Next is propped cantilever beam. Propped cantilever beam. So this is the propped cantilever beam. One end is fixed, another end is hinge or roller, whichever it may be. But this is the combination of cantilever beam, and here in case of cantilever beam, one end is free, but in case of propped cantilever, both ends are with support, but one end is always a fixed end. Then next part is static equilibrium equation. There are three static equilibrium equation. First one is summation of H equals to 0, means summation of horizontal forces which are on beam, summation of horizontal forces equal to 0. Second equilibrium equation is summation of vertical forces equal to 0. And third is summation of movement equal to 0. These are three static equilibrium equation, and on the basis of these static equilibrium equation there are two structure. First one is determinate structure and second one is indeterminate structure. In case of determinate structure, we analyze any kind of a beam with the static equilibrium equation. That structure is nothing but a determinate structure. Means the determinate structure is analyzed by static equilibrium equations, and second, indeterminate structure is not able to analyze completely by static equilibrium equation, not able to analyze completely by static equilibrium equations. Then second, SOM is depend upon determinate structure, because in case of SOM we deal with the structures which are determinate, means which are solved by static equilibrium equation, and in TOS we deal with that structures which are indeterminate, means not fully solved by static equilibrium equations. So TOS is for the indeterminate structures. And the examples for determinate structures are, or determinate beams are, simply supported beam, then cantilever beam and overhanging beam. Cantilever and overhanging beam. So these are the beams which are calculated fully by static equilibrium equations, and indeterminate are fixed beam, then next is propped cantilever beam, next is propped cantilever beam, and last is continuous beam. So these are the indeterminate structures which are not fully calculated by static equilibrium equation, because in these fixed propped cantilever and continuous beam there are reactions or number of unknowns are more than 3. Okay, so that's why we are not able to calculate the more than 3 unknowns by these 3 equations. So that's why this is under the indeterminate structure. And in case of simply supported cantilever overhanging, only 3 unknowns are there. But in case of overhanging, if there are a number of unknowns are more than 3, then also that overhanging comes into indeterminate structure. But but in case of overhanging beam, the unknowns are 3, then we use the static equilibrium equation to solve that beam, and this consider under the determinate structure. And one most important point about the simply supported beam, simply supported beam, in that simply supported beam, one end is hinge, another end is roller. If we take both the support as a roller, then that structure is unstable. Okay, and if we take that both support as a hinge, then also that structure is unstable. Okay, there are some rules for determining the stable and unstable structure. We discuss that rules in a further video or in a further slides. Next is type of load. So first one is point load or concentrated load. So this is the point loading or concentrated loading. Second is UDL, uniformly distributed load. So this is the uniformly distributed load. This is how it represent, and this is in, for example, this is in W per meter. Okay, and this point load is represented Newton. Okay, this is not in meter or anything. This is directly in a Newton, and this is in Newton. Okay, we take it as W Newton per meter. Okay, this is how the uniformly distributed load, and here we need to convert this loading into point load. So here we convert this as a Newton. Okay, so for that, this is the length of this span, and for converting this, first take this loading as W and multiply this by length. Then this is the point load, which is WL. So here WL is nothing but a point load, and which is in Newton. So this is how the uniformly distributed load, and by using this point load you can calculate or you can solve the further calculation. And then next is uniformly varying load. So uniformly varying load. So uniformly varying load is represent like this triangle, and this is the length, and here we also need to convert this triangular loading into point load. But, and one more point, this uniformly distributed load is put on half of its length. Always put it on half of its length. And here in case of uniformly varying load, always put that point load is h by 3 or L by 3 from this base side, means h by 3 from here and 2h by 3 from here. Okay, so how to convert this? So first, this is the W. Here the loading is present, and this loading, take it as a triangle, and the area of this triangle is half of base into height. So first, half into what is the base? This is W base, and divided by L. So this is nothing but a point loading for this uniformly varying load UVL, and put it on this point WL by 2. So this is how the type of loading, these are the three major loadings which are used in the calculation of bending moment and shear force. There are two important points, and there are very important points. We discuss that point in a further session or further slides, but this point is important, so I tell it here. So note that point. So first point is the bending moment at hinge is 0, means at hinge point the bending moment is always 0. And next, the point of contraflexure occurs in overhanging beam. Point of contraflexure. So we'll discuss all this point of contraflexure and bending moment further session in further session. But here remember these 2 points. In a bending moment at hinge is 0 and point of contraflexure occurs in overhanging beam. Overhanging beam. Okay. The next is first couple. Couple is that force which is equal in magnitude, but opposite in direction. And couple is itself a movement. First, equal in magnitude, opposite in direction. Second, couple itself a movement, and movement is nothing but a turning effect of a force. Then next point, turning effect of force. This is nothing but a movement. Movement is force into distance or force into perpendicular distance, and movement is also a couple. But in case of couple, the forces are equal in magnitude and opposite in direction. Couple is vector quantity. So in short, what is vector? Vector is nothing but the force which has a magnitude and direction both are vector quantities. Second, scalar quantities. Scalar quantities which has only magnitude, no direction. Then third is tensor quantity. So tensor quantity, first magnitude is there but directions are 2 in case of tensor. Then example for this tensor is stress and strain. So this is how the couple. And next is then shear force and bending moment. So shear force is summation of all the vertical forces. Summation of all vertical forces is nothing but a shear force. And bending moment is nothing but a summation of all the moments. Summation means addition. Addition of all vertical forces is shear force, and addition of all movements on a particular beam due to the vertical forces, horizontal forces and the movement, all the addition of these movements is nothing but a bending moment. Then second important point is sign convention. So sign convention for shear force are whenever the applied force is in vertically downward direction, take it as negative, and whenever it is vertically upward, then take it as positive. This is the sign convention when you calculate the shear force from left side of beam. And whenever you calculate from right side of beam, then take upward as positive and downward as negative sign. Okay, so here what is right side and what is left side? So right side means whenever you calculate the shear force from this point to right side, then take these sign convention, and whenever you start from this point and calculate in this direction, in left direction, then take this left direction sign conventions. The next sign convention for bending moment. So sign convention for bending moment are first, this is the same beam. Okay, if you calculate the movement from right side, then take it as this side, then take it as positive. From this, take it as negative. Here the clockwise is negative and anti-clockwise is positive. Okay, this is the beam, and if you calculate the bending moment, from this point, okay, from this point in this direction, then take these signs. Okay, these signs. Then take these signs. And if you calculate the bending moment from this point in this direction, then take these sign conventions. Okay, this will be confused right now, the bending moment sign convention, but by using these sign convention, the steps to find out the bending conventions are more easier than by hogging and sagging, as my point of view. So you go through this, or if you want to know about the hogging and sagging, we will discuss that too. So whenever the beam has these kind of sign convention, whenever the beam has these kind of sign convention, which is like hogging and sagging, hogging take it as positive, and hogging take it as negative, and sagging take it as positive. So these are the sign conventions for sagging. Okay, because of this force the beam get deflected downward side, so this is the sagging, and take it as positive. And if on this beam the direction of forces are like, or direction of movement are like this, then the beam get hog, and due to the hogging the take the movement sign convention as negative. So these are the hogging, sagging and the sign conventions for bending movement. Then next is, okay, this is a chart for shape of shear force diagram and bending moment diagram. As you see, the shear force and bending moment, shear force is summation of all the vertical forces and bending moment is summation of all movements. After calculating the shear force and bending moment, the work is to draw a shape of shear force diagram and bending moment diagram. For that there are some rules. For different loading there is a different kind of shape for SFD and BMD. So if in on the beam there is no loading, means no loading, the span is empty, then the shape of SFD on that beam is straight line. Okay, then the SFD for no loading is straight. For BMD the line is inclined, so here draw a inclined line for BMD in case of no loading. Then second, for UDL, for uniformly distributing load, the line is inclined for the shape of SFD and 2D parabola, and 2D parabola for BMD. Okay. Then for UVL, uniformly varying load, 2D parabola for shape of SFD and 3D parabola for BMD. 3D parabola for BMD. The next loading is point loading. So for point loading, a vertical bluff means vertical line for shape of SFD, and there is no effect, in case of BMD. Same as in case of couple. In case of couple, there is no effect in SFD, but vertical bluff in BMD. So this is how we can draw a SFD and BMD by using these simple rules. Then next is, then there are some important points. Please note that points. First point is contra shear, and second point is contra flexure. So contra shear is related to shear force, contra flexure is related to bending moment. If shear force changes its sign, then that point is called as contra shear, and if bending moment changes its sign, then that point is called as contra flexure. Changes its sign means from positive to negative and from negative to positive. This is the conversion of shear force and bending moment diagram. Then one more point is important. If on any point shear force is minimum, then on that same point, bending moment is maximum. Bending moment is maximum. These are the important points. Remember these. And one more point is that the span on which shear force is constant. Shear force is constant, then that span is shear span. And if on any beam, if bending moment is present, if only bending moment is present, and there is no shear force, then that condition is pure bending condition. Then that condition is pure bending condition. So all these points are important. The next point is important cases in overhanging beam. There are two conditions in overhanging beam. First condition, the whole span is L, and the span from this roller support to end is A, and from this hinge to end is A. So remaining is L minus 2A. And in second case, the total span is A plus L plus A. Okay, L plus 2A is a total span. These are the two conditions in case of overhanging beam. So here we see what the value of A for different conditions or different length conditions. Okay, in first case, the bending moment is positive bending moment is equals to negative bending moment. First, maximum positive bending moment is equals to negative or maximum negative bending moment. This is the condition. Okay, in that this condition is nothing but a economical beam. This is economical beam. This is first condition in case of case 1. If that condition happens, means the bending moment is like this. Means positive and negative bending moment are equal. In that condition, A is equals to 0.207 of L. This is the value of A. And they directly ask this kind of beam they given, or they ask that maximum positive bending moment equal to maximum negative bending moment in case of overhanging beam. A is equals to what? So A is equals to 0.207 L in this case. Second case is total negative bending moment. Total negative bending moment. So total negative bending moment diagram is like this. Means total bending moment part is in negative case. So this is the BMD, and value of A is L by 4. So this is the value of A here. Then second condition. In second condition, you see the value of length A, L and A. Okay, here the value of A is equals to L divided by 2 root 2. So these are the different values of A for overhanging beam with different length conditions, with different bending moment conditions. And this is the important question. Important question. Remember this question and values of A for different conditions. Relation between bending moment, shear force and load intensity. Derivative of movement is nothing but a shear force. And derivative of shear force is nothing but a minus of loading. So this is the relation between shear force and bending moment and load intensity. Then there are some extra points. So here we discuss the weight comparison between square, rectangle and circle. So the weight of rectangle to the weight of square is equals to 0.79, and next the weight of circle to weight of square is equals to 1.11. So these both are important values, and this question is also asked in exam. The next question or next point is, then second extra point is, here the square section is given. In the first figure a square section is given, and in second figure same that square section with same weight and same area. But in first figure the sides of the square are horizontal and vertical to the given line, and in second figure the diagonals are horizontal and vertical to the given line. Okay, and here we need to find the moment resistance for both of the figures, and the moment resistance for first figure represent as M1. This is M1, moment of resistance for first figure, and moment of resistance for second. So ratio of moment of resistance. Moment of resistance of first means the square which has a horizontal and vertical sides of square. The moment of inertia of first is larger than the second, which is by root 2. Okay, so m1 is root 2 times larger than m2. Means moment of inertia of first square is larger than the moment of inertia of second. Then the next point is flattering section. Flattering section, in that flattering section we cut the uppermost part of any figure. Here first figure is with diamond shape and second is for the circular figure. So in case of diamond shape we cut this a by 9, means total is 2a, side is a. Okay, so here this is a up to this point, from top to here the value is a, and this cutted portion is a by 9 and remaining portion is 8a by 9. So this is the flattering section for diamond, and by cutting this dash part from top and bottom, then strength is increased by 5.37%. Strength increase by 5.37%. Same in case of a circular section, if we cut this part called as, and cutting of this part called as flattering, and if we cut this part from top and bottom as 0.011d, diameter of 0.011d, then the strength is increased by 0.7%. Strength increased by 0.7%. Okay. The next fourth point is strongest beam from circular log. Strongest beam from circular log. Here we cut a rectangular part or rectangular beam from a circle and then find out the values for it. Okay, here we consider this is the circle and we cut a rectangular portion from this circle. Okay, this section here, h is the height for rectangle, b is the width for rectangle, and d is the diameter of this circle. Then here the values of h by b is equals to root 2. H by b means what? Height of height of rectangle to the width of rectangle ratio is root 2. Then d by b, the ratio is root 3, and then h by d, the ratio is root 2 by root 3. So these are the three values, and all the three values are important, and this question is mostly asked in the exam. Then next is slope, deflection and movement chart. So in that, first is the cantilever beam with UDL, second cantilever beam with point load, third cantilever beam with UDL, fourth cantilever beam with UVL, then fifth is simply supported beam with point load, and sixth is simply supported beam with UDL. Okay, movement of these beams are first movement. First, here in the cantilever beam there is only moment, so moment is m. Second WL, third is WL square by 2, fourth is WL square by 6, then fifth is WL by 4, then sixth is WL square by 8. Okay, these values you need to remember these values. And for slope and deflection there is a one trick, which is for slope, the slope represented by theta. Okay, so here for first ml by ei, then for second take ml by 2 ei, then for third take ml by 3 ei, then for fourth ml by 4 ei. Then reverse for simply supported. Theta equals to ml by 4 ei and then theta equals to ml by 3 ei. Just put the values of movement into the m in this theta equation. So you get the values of slope. And then next, in case of deflection, so in case of deflection the values are delta is deflection, theta is slope. Just multiply that theta with L by 2 for first condition, then 2L by 3 for second condition, 3L by 4 for fourth condition, 4L by 5 for fourth condition. Then for simply supported, multiply by L by 3. Then for fifth or sixth condition, for UDL, multiply by 5L by 16. Okay, so these are the deflection value. Just put the values of theta into this and multiply with the factor given here. So you get the values of deflection. So these are the deflection and slope chart. Then next is distribution factor. Distribution factor is a ratio of stiffness of that member to stiffness of that joint. Distribution factor is stiffness to summation of stiffness ratio. This is the distribution factor, and distribution factor in case when far end is fixed, then the stiffness is 4 EI by L, and if the far end is hinge, then stiffness is 3 EI by L. Okay, these are the values of stiffness. Then next is fixed end movements. Okay, then next is fixed end movement. In the first condition of fixed end movement, the beam is subjected to point load at its center, and for that fixed end movement about A support, that is MAB, movement at AB is minus WL by 8, and for fixed end movement at MBA, means at the support B, is plus WL by 8. Then same for second condition. Here also point load is given, but that point load is on a eccentric loading, means on the left side the span is different and on the right side the span is different, and this is the formula to calculate the fixed end movement for the support A and B. Then third condition, fixed end movement for the beam which is subjected to UDL for whole span. Fourth condition, subjected to UDL but about the span A. Then next condition, subjected to UVL about whole span. Then next condition, subjected to UVL up to span A. Then seventh condition, UVL on whole span but in triangular portion or in a triangular condition. Then next, subjected to movement about the beam or the fixed beam, subjected to movement about its center, and next subjected to movement, but this movement is eccentrically acted on this beam. So these are the fixed end movement for the support A and for support B, and these all the fixed end movements are important, and most of the questions are asked from this part. So from first, then third and fifth, and this second, these are the four conditions. The four formulas are important, where and so before discussing principal stress, there is one more term which is principal plane. Principal plane, and that principal plane is nothing but on the principal plane there is only normal stresses. Normal stresses are present on principal plane and no shear stresses. That kind of plane are called as principal plane. Okay, normal stresses present, no shear stresses. Then principal stress. Principal stress is magnitude of normal stress. Magnitude of normal stress acting on principal plane. This is called as principal stress. Then there are two terms, which is major principal stress and minor principal stress. So major principal stress, the maximum value of normal stress is called as major principal stress, and minimum value of normal stress is called as minimum principal stress or minor principal stress. Okay. Then next term is major principal plane and minor principal plane. So major and minor principal plane are that plane carries major and minor principal stresses are called as major principal plane and minor principal plane. So these are the four terms. Principal stress is the magnitude of normal stress acted on principal plane. Principal plane is what? Principal plane is that plane which carries only normal stress, but it doesn't carry the shear stress. Then major and minor principal stress. So major and minor principal stress is maximum and minimum value of normal stress is nothing but a major and minor principal stress. Then major and minor principal plane. Plane which carries maximum or major value of principal stress is nothing but major principal plane, and which carries a minimum value of principal stress. That plane which carries a minimum value of principal stress is nothing but a minor principal plane. Then next is, then next there are two methods to find out the stress transformation. First one is analytical method, and that is calculated or that perform with the help of formulas. And second one is graphical method, that performs with the help of Mohr circle method. So in case of analytical method, there are few important formulas which I discuss here. So first formula is principal stress. In the principal stress, we calculate that principal stress on two axes, okay, x and y. So first, for sigma 1 or sigma 2, the formula is sigma x plus sigma y divided by 2 plus minus square root of sigma x minus sigma y by 2 whole square plus tau xy whole square. Okay, so this is the formula for principal stress. If we take the plus sign here to calculate or to solve this formula, then this is major principal stress, and if we take the minus here, then that formula is for minor principal stress. Then next formula is absolute maximum value of shear stress. Absolute maximum value of shear stress. So absolute maximum of shear stress formula is tau max is equals to sigma 1 minus sigma 2 divided by 2. Then normal stress acting on shear plane is sigma x dash or sigma y dash, which is equals to sigma x plus sigma y by 2. So these are the formulas to calculate the stress transformation in case of analytical method. The next formulas are, next formula is about the pure shear condition. In case of pure shear condition, the normal stresses about x and y axis are 0. So the normal stresses and shear stresses in pure shear condition are sigma theta is equals to tau sine 2 theta, and shear stresses tau theta is equals to minus tau cos of 2 theta. So these are the two formulas used in a pure shear condition. So this is the one more important condition, which is about the principal plane and shear plane. So principal plane and shear plane are perpendicular bisector to each other. Perpendicular bisector means 45 degree to each other in each and every case. Principal plane is perpendicular bisector to shear plane, and this is the important condition. On this point, many times they ask the question that principal plane and shear plane is bisector by which angle, or perpendicularly bisect, or by 60 degree bisect, or by 45 degree bisect. So the answer is 45 degree. The principal plane and shear plane are perpendicular bisector to each other. Then second method is Mohr circle method. So Mohr circle method, first formula in the Mohr circle method is about the center of Mohr circle. So first center of Mohr circle is find out by this formula. Sigma average is equals to sigma 1 plus sigma 2 by 2. So these are the normal stresses at first point and second point. Taking average of these two normal stresses, we get the center of Mohr circle. Then this is the formula to calculate the radius. R is equals to square root of sigma x minus sigma y divided by 2 whole bracket square plus tau xy square. So this is the formula to find out the radius of Mohr circle. Then next, the formula to calculate the maximum shear stress. So that is sigma x minus sigma y by 2. So these are the important formulas from Mohr circle, and these 7 to 8 formulas are enough in case of principal stresses, and these all are important formulas. So remember all the formulas. Each and every formula is asked in exam about the analytical and Mohr circle method. Then bending stress in a beam. So bending stress in a beam, there is one formula to calculate the bending stresses, which is M by I equals to sigma by Y equals to E by R. So in this formula, the M is bending moment, I is moment of inertia. So to calculate the bending moment, we use this formula. Then moment of inertia, sigma is a bending stress. Then Y is the distance from the neutral axis to the fiber which we want to calculate the bending moment, and E is the Young's modulus, and R is the radius of curvature. So this is the formula to calculate the bending stress. Then by using this I and Y max, here we calculate the section modulus. So section modulus is I by Y max, and the section modulus for the section I and rectangle and circle, comparing these three sections, the section of I for the section modulus, the higher the section modulus, more is the strength. So higher section modulus is for the I section, then for the rectangular section, and then for the circular section. So for higher section modulus, there is higher strength. Then next is bending stress in a composite beam. Composite beam is that beam which is made by two different materials. So here this is the beam or the composite beam made by steel and wood. If we calculate the modular ratio of the composite beam, then the formula is ES by EW, means ratio of Young's modulus of steel to the Young's modulus of wood is nothing but a modular ratio. So here this is the beam made by steel and wood. If we convert this beam wholly into steel and wholly into wood, then what is the difference between the area of the member or the width of that member? So here steel is as it is in the first diagram, and second here this is the wood. If we compare the wood with steel, wood has a more area required to resist any kind of load. Okay, and as compared to steel, steel require a less area because steel is more stronger than a wood. So here steel is take by reduction of width. So here we convert the weak material to the stronger material. So the area of that strong material will be m times of its original area. And in next, if we convert this steel into wood, okay, wood is as it is in this diagram, but steel carries a more load in a lesser area. But in case of wood, we need a more area to carry that kind of load or that particular load. So here we increase the area of this wood. So here the area, if we convert this strong material into the weak material, then area will be 1 by m times of its original area. So this is about the composite beam. Then next is shear stress in a beam. To calculate the shear stress in a beam, we require the shear force, then area, then width of that section and moment of inertia, and Y bar. Y bar is the distance between neutral axis of that section to the fiber where we want to calculate the shear stress. So this is the formula to calculate the shear stress, which is SA Y bar divided by BI. So how to remember this formula? So if you read this formula as a sentence, then you get a sentence as a say by. Okay, so this is the formula to calculate the shear stress. You can remember like this, that say by is the formula to calculate the shear stress. Then next is shear stress distribution. To know the concept behind shear stress distribution, here we discuss four sections. First one is rectangular, then solid circular section, triangular section, and diamond section. So in case of shear stress distribution, we find the shear stress which is maximum or minimum on which point on this section. So here in case of rectangular section, the tau max is present about its neutral axis, which is 1.5 tau average. And Tau average is nothing but S by BD. S is the shear force and BD are the dimensions for this rectangular section. So here BD is present in case of rectangular section, but in case of circular section, diameter is present. In case of triangular section, height and base is present, like that. Okay. Then next, tau means the shear stress is minimum about its ends. Means last fibers the shear stress is 0. Then in case of solid circular section, the tau max is present on neutral axis, which is 1.33 tau average. Okay, so here tau average is nothing but S by BD, means S divided by area. And same like rectangular section, the shear stress is 0 about its end in case of circular section. So this is the important formulas. Tau max is 1.5 tau average for rectangle. Tau max is 1.33 tau average for this solid circular section. Then next, in case of triangular section, there are two values of shear stress. First, the maximum value is about its center, and about its center means the center for this rectangular section is h by 2 because total height is h. So about the h by 2 means about the center, the tau max is maximum, and that tau max is nothing but 1.5 tau average. And there is one more value is present about the shear stress, which is on neutral axis. Okay, in case of rectangular section and circular section, neutral axis and center is same, but in case of rectangular section both are different. So here the rectangular section neutral axis is h by 3 from the base, and for this the shear stress is 1.33 tau average. Then in case of red diamond section, both values are there, values about its center and value about its neutral axis. So value about its neutral axis is equals to tau average, and value about its middle point of its half section is 9 by 8 of tau average. Okay, so that value from the top end of this diamond section is 3h by 8, and this remaining is h by 8. So total is h. This is h by 2 and h by 2. Okay, so these are the values for the shear stress distribution for all the four sections. Then next is torsion in a staff. So staff is the machine which is used to convert the energy from one form to another form, like by twisting or by torsion. So this is the formula to calculate the torsion. So T by J. T is nothing but a torsional moment. J is the polar moment of inertia. Then tau is the torsional shear stress, R is the radius of curvature, G is the shear modulus, theta is the angle of twist, and L is the length. Okay, so here numerical is asked rarely, but they ask one formula about this formula is what is GJ. So GJ is nothing but, take this first term and second term. So GJ is nothing but TL by theta. So this GJ and TL by theta is nothing but torsional rigidity. So they ask what is torsional rigidity, or in the previous video we see the axial rigidity and then flexural rigidity. So these all rigidity formulas are important. So here GJ is nothing but a torsional rigidity. Then one more term is there, torsional stiffness. So torsional stiffness is nothing but T by theta. So here T by theta, if we take this theta into this side, then formula for T by theta is Gj by L. So this is the torsional stiffness. So these two formulas are important, and these formulas are formed by this torsional equation. Then next is combined effect of bending and torsion. To find out the combined effect of bending and torsion, there are two formulas which is related to bending stress and torsion stress. So that two formulas are M by I is equals to F by Y equals to E by R. And next for torsion, the formula is T by J equals to tau by R equals to G theta by L. So these are the two formulas here. But in the first case, in the bending stress, the value of section modulus is related to moment of inertia and Y max. In second case, the section modulus is related to polar moment of inertia and Y, or here the distance is R. Okay, here they choose the distance between neutral axis and the point where we want to calculate the torsional stress. The distance is R here. So the section modulus in first case and second case, the difference is about the moment of inertia. So first, in case of circular section, for example, in case of circular section, I, that is moment of inertia for circular section, is pi d raised to 4 divided by 64. But the polar moment of inertia is the addition of two moment of inertia, which is about x-axis and y-axis. The addition is pi d raised to 4 divided by 32. Okay, these are the values of section modulus. And here we want to calculate the sigma b. So the notation for sigma b in this formula is F. So F is nothing but sigma b. So to calculate sigma b, the value is m divided by z. And to calculate tau max, the formula is T divided by z. So by putting the values of polar moment of inertia and simple moment of inertia in this formula, the value for sigma b is nothing but m divided by pi d raised to 4 divided by 64 into this y bar is d by 2. Here in this case, t divided by pi d raised to 4 divided by 32 into t by 2. So the values after cancelling the equal portion, value for sigma b is m divided by 32 32m divided by pi d cube divided by 16t divided by pi d cube. So the ratio of sigma b and tau max is 2m by t. Okay, but in some case, if this m means moment of inertia or bending moment is equals to the torsional moment, then the combined effect of this bending and torsion are twice of its values. So sigma b is equals to twice of tau max if values of m and t are equal. So this formula is important, that relation between m and t is equal, then sigma b is equals to twice of tau max, and this formula is also important, that 2m by t. Then next is method of slope and deflection. So there are 6 methods to find out the slope and deflection. First one is double integration method. So to calculate the double integration method, here the condition is there is uniform bending moment equation. Uniform bending moment equation. Then next, no point load, and third one is no couple acting on this span. Okay, they mention these three condition or one of the condition from these three. So and they ask which kind of method you can use for solving the slope and deflection here. So these are the three conditions in case of double integration method. Then next is Macaulay method. Macaulay method is the modified form of double integration method. Double integration method. And in case of Macaulay's method, the bending moment equation is changed from one form to another form to solve any kind of span. Then next, in case of moment area method, conjugate beam method and strain energy method, one condition is always they ask which kind of beam is solved by these three methods. So prismatic and non-prismatic beams are solved from these three methods. Then next, last one is superposition method. If any kind of load acting on a beam and which is more than two point loads or more than two UDL and UVLs are acting on a span, then this superposition method is used. So these are the 6 methods, and mostly they ask about the double integration method and Macaulay's method. Then next is column and struts. So in the first figure, the column is there, and column is a vertical component which is subjected to compressive loading. Then next is struts. Struts are the inclined members which are also subjected to compressive loading. Struts we use in a steel structures or in case of construction of trusses, and we use these columns in case of RCC structure. So there are three type of structures or three type of columns. First one is long column and second one is short column, and both are generally used. But third one is intermediate column, which is not used, or most frequently it does not use. So first one is long column. Long column has a low load carrying capacity, and long column fails due to buckling. So here low load carrying capacity and fails due to buckling. In case of short column, here high load carrying capacity is present, and these columns are fails due to crushing. And then next is intermediate column. Intermediate column is frequently used and it fails due to both buckling and crushing. Then next, here in case of columns, one thing is important, which is effective length. So based on effective length, the strength depends. So to find out the effective length, here we take a 4 sections. First is with hinge support. So for hinge support, the L effective is L. Then in case of hinge support at one end and fixed at another end, L effective is L by root 2. Then third, one end is free, another is fixed, then L effective is 2L. And if both end are fixed, then L effective value is L by 2. So these are the effective length for different supports of the column. And then slenderness ratio. Slenderness ratio is denoted by lambda. Lambda is equals to L effective divided by R minimum. L effective is effective length. R minimum is radius of gyration. So radius of gyration is find out by the formula is square root of I by A. So this is the formula to find out the radius of gyration, and slenderness ratio is depend upon the effective length. If effective length is maximum, then slenderness ratio is maximum. If radius of gyration is minimum, then slenderness ratio is maximum. Then last point from the strength of material is kern of the column. So kern is nothing but that portion in a column where no tension act. Okay, so to find out that tension free section from the column, the eccentricity is used. So with the help of eccentricity, we get the kern value. So first, in case of circular section, the eccentricity is d by 8 from its center. Okay, if we draw the circle from the eccentricity value, then we get that kern portion. So in case of circular section, we get kern as circle. In case of rectangular section, we get kern as a rhombus. Same, in case of I section also, we get a kern as a rhombus. In square section, square as a kern, and in hollow circular section, circle as a kern. So these are the different values of the kern given here. With the help of eccentricity, we calculate the kern dimensions. So these are the kern values, and mostly they ask the kern value related to circular section. So for kern of circular section, the value is d by 4. Or they ask what is the formula for the circular section if diameter is 10 mm, then find out the eccentricity and kern for that. Or else they ask for a rectangular section.